Hello. So now that we have gone over what really is light and thinking of the idea of light being this electromagnetic radiation, energy in the form of a wave, that helped us to understand where electrons are in atoms better. Now we know that electrons can only exist in these specific energy levels, that there's a pretty firm order as to where the electrons are in an atom. And we're moving into really discovering what our current model of where the electrons are in atoms. And in order to understand that, we need to go a little bit into the realm of quantum mechanics. So really looking at some of the advances that physics has taken in the past 100 years, which is a lot of ideas that are complex, that seem to not make that much sense, because from what we observe in everyday life, we don't see any evidence of this. But through experiments that are complicated and difficult to do, there has never been an experiment that has disproven quantum mechanics or quantum theory. So the first thing that we're going to look at is the photoelectric effect. This is this often comes up in trivia when people ask, what did Albert Einstein win the Nobel Prize for? Oftentimes they think it's his most famous idea or his most famous formula, E equals mc squared, and that's not it. He won the Nobel Prize for the photoelectric effect. So what is the photoelectric effect? Well, scientists have been looking at this for a while. It's this idea that if you shine light, and that's what this red arrow, red squiggly line here is symbolizing. If you shine light on a piece of metal, sometimes if the wavelength of the light is just right, you can then get the metal to release an electron. An electron will be bounced off of it. So the photoelectric effect is this phenomenon in which electrons are released from a material when it absorbs light or electromagnetic radiation. So this idea of the photoelectric effect, there's many instances where this has been seen. This is part of how a photovoltaic solar cell works. You know, if the little guys in the back of my room, the light hits the little solar cells, and that produces a stream of electrons called an electrical current that runs a little very low power motor that's in there. So what does this have to do with electrons in atoms? Well, okay. So Albert Einstein proposed this idea, and because of this, you know, if you just shine light on particles, nothing happens. I mean, right now, you know, it may get warmer, but the particles don't necessarily move. So, but if you were to, instead of thinking as light as a wave, if you start to think of light as an actual stream of particles, then it can sort of make sense why the photoelectric effect would happen. So think of a table that is just filled with ping pong balls. And if I shine light on those ping pong balls, does anything happen to them? No. But if I were to throw a ping pong ball at the table, yeah, those ping pong balls would work. So maybe we can start thinking of light less as a wave and more like a particle. And that's what Albert Einstein did. He said that we can actually think of light as a stream of particles, and he called those particles photons. And the energy of each photon could actually be calculated by looking at the the wavelength or the frequency of that. It's related to energy through the same formulas that we were using at the beginning of the chapter. And through this, Einstein, came up with a bunch of other really forward-thinking ideas, and one of them was his idea of special relativity. And in that, he said that energy can be converted to mass. And there's that very famous formula that we all attribute to Albert Einstein, E equals mc squared. And we could rearrange that for mass, that we can calculate the mass of a specific quantity of energy. And this suggests that so light has energy, and what he is saying is that, well, if light has energy, then it must have mass, and we can't measure the mass of light. Those two things seem to not be able to exist at the same time, and he is saying, yeah, they can. He says that photon particles of energy have some sort of mass, and that's really crazy. That particles, we think of particles as having mass, and we think of light as being something completely different, pure energy, no mass. He was saying that those two things can be converted from one another, that energy can be converted into mass and mass can be converted into energy, and therefore they are essentially two different forms of the same thing. So after Albert Einstein came up with this idea that maybe light can be thought of as a particle, we sort of turned that around and said, well, if light can act as a particle, that's what the photoelectric effect, one way of interpreting that photoelectric effect, then can matter, such as an electron, which we've always thought as a particle with mass, can that be thought of as a wave? And your first instinct is probably like, well, no, we know an electron is it's a really small thing, but it's matter. It's just a smaller version of, if you take a human being and you make it, the smallest thing that makes up that is an atom, and then you go one step smaller and one step smaller and one step smaller, you get to electrons. So it has to have like mass and a size, and it's not a wave. A wave has all sorts of weird properties, like what's the location of a wave? A wave is always moving. And so another experiment was completed to sort of try and figure that out. Is an electron a particle, or is an electron a wave? So this was called the double slit experiment. And in the double slit experiment, they sent a whole bunch of electrons, particles, through a barrier with two small slits in it. And if electrons were actually particles, this is what we would have expected, that an electron would hit the barrier and not go through, or an electron would go through those two barriers, and you would see where the electrons landed on the other side. When this experiment was actually done, what they saw was this pattern, which is called an interference pattern. You saw that not only were there electrons on the backside, but these electrons were exactly behind where you would expect there to be no electrons. And the only thing that we know that causes this interference pattern are waves. So this was the big the big result of this was the idea of maybe we should start thinking of electrons as waves. When we do that, when we think of electrons as waves, it is going to pose a whole bunch of other questions, because we're looking to be able to predict exactly where an electron is. If you think of an electron in a similar way to the planets are orbiting around the sun, we're able to predict exactly where planet Earth will be 500 years from now. Now that we have resigned to the fact that we can also think of electrons as waves, we can't predict the location of a wave. So that's going to sort of turn our question even on its head. The big question of where are the electrons and atoms becomes sort of suspect. Maybe that's not a question that we can ever answer. And as it turns out, that pretty much is a question that we're not going to be able to answer. And we're going to learn what do we do instead? Instead of saying exactly where electrons are, we instead just say where they can be found, most likely to be found, orbiting around an atom. We're not actually going to get a definitive answer to that.